Mathematical proofs, natural questions, and the pi1 lattice.
Okay, so this is going to be a rambling talk, but it's going to be about effectiveness nonetheless. So the wouldn't be very effective, but the topic is, and I'm honored to be invited to speak here at this conference in the honor of my friend, since I came to New York, Sergey, who has done very impressive work in this intersection of logic and computer science. And I think that the talk is really in the same spirit, because I'm going to talk about a period. I mean, I'm going to go further than that, but I'll start with a period in which really the two things came out very nicely, and this is Gödel's proof of the completeness theorem, which is also the source of the undecidability results. And this, by the way, was the first time, as far as I know, that we had really a discussion that a proposal, how to define recursive sets, and he gives in this paper a particular proposal, very precise proposal, which eventually turned out it defines primitive recursive, it doesn't define the recursive sets, but still you see how this, in this period from, say, let's start at 1925 up to 1950 or something like this period in which logic and computer science were very much integrated. Okay, so I think this fits very well the topic of this symposium in honor of Sergey, and I'm very happy to present some ideas about it, but mainly it's going to be the talk in the philosophy of mathematics, and the title gives you the three parts of the talk: unknowable mathematical truths, the question of natural questions in mathematics, and then there will be some addendum, which is a technical part, and it is some questions that arose out of these ideas. And I must say, I'm not an expert in this domain. I think there are people here who might answer some open questions, and perhaps this is a good opportunity for me to find out if some of the results of the questions are known or have been posed before. I mean, I wouldn't be surprised if they have, because to me they seem natural questions. Okay, so let's start where it started, and this is a famous quote from Hilbert, in which it says that in mathematics there are no ignorabimus. That means here you have a mathematical problem, think about it, solve it. And in principle, you should be able to solve it. And although now everyone knows this is wrong, but in a way, I think mathematics continues in the same spirit of Hilbert to nowadays. The idea being that if you have something which is posed by a mathematician, which is the domain of human thought, what human thought asks human thought in the pure domain of thinking should be able to solve. If it's a good question, it should be accessible to that. I mean, there should be no mysteries there. So in physics, of course, there are mysteries, and we are willing to accept them on everyday level. There are truths which are knowable, unknowable truths of physics. Here is an example of an unknowable truth of physics. I take here a quarter, and I toss it. Did it fall heads or tails? Now I toss it again, and then nobody will know the answer to the first question. Okay, so we create mysteries in physics on everyday level. And we don't have to go, I mean, we can speculate, can we deduce from the state of the world in 50 years, what was this, can we do it or not? But our everyday intuitions of the common man and so on, yes, of course, in physics you cannot do. But how can we have mysteries in mathematics? This is really a mystery itself, because there it's all supposed to be purely non-empirical. Okay, so this was Hilbert's thought. Now, let me just point to it that the whole thing The method this was done by Gödel is a method of self-reference. You have names and object functions, and you substitute the name inside the functions. You have functions which apply to their own names, and this is the famous diagonalization method, and you can see how it follows very closely from Cantor's diagonalization. And here perhaps I want to give a characterization of mathematical logic. We spoke about the characterization of a quantifier, so let me just give a general hand-waving characterization of mathematical logic. It is a discipline that uses systematically the naming relations, the relation between the name and what it is the name of. And you can see that it applies to the general way in which mathematical logic traditionally it was proof theory and model theory and set theory. Proof theory, recursive was a proof theory. Set theory, model theory. Nowadays this is old-fashioned and so on. But in all these domains you see that all of them involve this. So this I would propose, if somebody asks me what is logic, I would say what is mathematical logic? Mathematical logic is that discipline. And to the extent that it goes away and forgets it, it becomes more and more integrated into the rest of mathematics, which can happen in model theory. Okay. Now, just to sum up the historical facts, and this was intended for a broad audience, then we have PA would be Peano's arithmetic, or the language of Peano's arithmetic. Delta zero, well, formula with all quantifiers bounded. Pi 1, well, it's a universal universally quantified pi 0 formula, and the sequence, I mean, the upshot of the results is that the sequence of pi 1 sentences is not CE, not computable enumerable, and not ARI, I would say, but this is old-fashioned in some cases. The sequence of all sentences where P is a Diophantine polynomial with integer coefficient, all of these true sentences is not Diophantine sentences is not CE. And similarly for other types of statements asserting universal generalization of easily checkable statements. For example, that a Turing machine on a given input does not halt in smaller or equal than n steps, and you just quantify over the n, and you get something, and you get statements which are not the sequence of all these true statements is not CE, or that a given multipartite linear function over the natural numbers does not converge on a given input in smaller or equal than n iterations. This is just last week we had a nice talk by John Conway about exactly this kind of problem, which is very, very nice, and again, the same phenomena takes place there. Okay, so this is what we by now know the easy undecidability results, because this is nothing more than the halting problem and the standard commonplaces examples and so on. And of course, in set theory, we have much more dramatic developments. But I'm not going to argue that it is just these results which gives us should give the mathematicians, or give the mathematicians the most worry. And the other results, I'll have something to say about the other results, but I want to focus on these results. Now, we have a deductive system, and the proof theoretic implications is that whenever you have a deductive system, and whenever there is an effective way to checking for every candidate for a proof, whether it is indeed a proof of this, you should be able to check it effectively, then all this, there is a sequence of all these formulas such that they are true formulas, but there is no proof of them for any given particular theory which satisfies this condition. Okay? So the whole thing is that we cannot know because we cannot prove. Now, Okay. Now, what does this mean? That there are unknowable mathematical truths, unknowable by humans. Why should this bother us? Okay. Gödel certainly was bothered by it because he wrote in 1951 a long paper exactly about this, and in which made a lot of speculation, and he was clearly worried by this fact. On the other hand, here is a quote from Shelach, and this is exactly the fonts are exactly reproduced there with the emphasis, with one of the sections, the glory of proven ignorance, to show that we cannot know. Okay, so this is the crown of a mathematical achievement, to show that we cannot know. Now this might be good in set theory, but I don't think to show that we can here something else takes place. Okay, now there are 6 points to clarify, and I want to rush through them very fast because I have limited time. First, mathematical knowledge requires proof, which can be formalized in an acceptable deductive system. Or does it? Do we really need proofs? Because this is the basic of the whole phenomena here, that we need proofs in order to know. And I want to speak about to know in a somewhat general philosophical sense. Perhaps in the absence of proofs or disproofs, the very question about the truth or falsity of phi is meaningless. There is nothing to, there is no answer because you don't have a Platonist world, you don't have a realist conception, so you say it's meaningless. That's one way of doing it. This is the second point. And so far the result does not point to a particular, because in the Gödel construction you don't get a particular one in which you don't know, because actually the sentences which you know that they are true. But, I mean, you know by a little reflection that the sentences are true. But what is the worry here is that there is a sequence, infinite sequence, and you cannot recognize them. And you know that a lot of them, infinitely many of them, will be true, and you won't be able to prove them. So since we don't have a particular one, the worry is not well grounded. 4, the results to have holds only with respect to any given particular theory, but theories can change. So perhaps we don't know now, we'll know it tomorrow, and so on and so forth. Perhaps there shouldn't be a big thing about it. And 5, perhaps the unprovable things are simply too long. I mean, you give me something and people said the Gödel sentence is so long, it will take a book to read it. Who will bother? Perhaps, so it's a limitation of human capacity, but it is simple limitation of length. So we might forget about it. So I will give to all of this, I will give my own answers here. And the answer to the first one, yes, it does. We must have proof. And perhaps in the absence of proof or disproofs, the very question can be meaningless. I would say no. In the case of pi1 sentences, you cannot just say the question is meaningless. And the result does not point to any particular sentence. I will say yes, but this doesn't avoid the problem. 4, what about speculations that in the future we can solve everything? I would say very doubtful. Perhaps the unprovable things are too long. The answer is simply no, they are not too long that we cannot read them. We certainly can read them. And we cannot understand them, we cannot figure them, but certainly it's not a question of not being able to read them. And the last, I would say, perhaps the questions are simply unnatural, weird questions and so on. And if you have a natural questions, this will be answered. That I don't know.
Well, you set up my talk. You just set up my talk. Thank you very much.
Sorry?
No, thank you for the introduction.
So, well, I hope we'll diverge later. But yes, and I want also to say that this is, that Conway's talk last week was a perfect way. I mean, I agree with everything that he said, and my points here are really to emphasize how much he was right. And I had submitted this title before I heard Conway. So it was simply a happy chance, okay? And Melvin can testify that it was to BA for a long time, but last week before the talk I submitted this title, and just by accident I happened to hear his talk, and I agree with everything he said. So the first is the sources of mathematical reasoning. Why do we need proofs? Okay. Because I don't think that mathematics is a mere formalism. We start with meaningful structures. And this is a big subject, and I don't want to go here in details, but mathematics is about the way we organize our world and our activities in it. Mathematical reasoning is based on capacity to recognize these basic organizational patterns, to grasp their general principles, and to follow their underlying rules. And the philosopher will underlying rules, we'll say Wittgenstein's rule following, which is a basic in all this. I mean, we recognize the structure, and this can be demonstrated with many, many problems which don't need any proof, but a kind of reasoning, and the answers is certain. It's more certain than any formal derivations will provide. And these are answers, finite or combinatorial problems, various styling problems. You show directly that difficult questions can be shown. There is no tiling of this board. You give a short argument for that. It's as certain that here you have reached rock bottom. I mean, it's as certain as you can imagine. Or, for instance, this Königsberg bridge problem, which you give Euler gave an argument, a decisive argument, even although the notion of graph wasn't exactly known there, obviously the argument is decisive and it proved the claim. Some problems concerning games are of the same nature, and some problems in intuitive probabilistic reasoning have this nature. That even if you don't, before you know the Kolmogorov axioms, you say, okay, I don't know what this formal setup would be, but this should hold. So it's a kind of a constraint on the axioms to justify this reasoning. And this reasoning is certain. So why do we need proofs? So the need proof comes from, I think, three sources. First of all, proofs, and the language of proofs organizes. We know we can speak with each other and know that we are speaking about the same thing. That means if I make a claim based on my intuitions and you make a claim based on your intuitions, we can go and cut the whole thing into little pieces and find out who was right. So in order, if you have claims that somebody made an error, and we always made an error, the way to verify it is a proof. There is no other way to do it. And this is a systematic way of error correction. In mathematics, somebody estimated that every year there are thousands of errors published in mathematical papers. Most of them will go unnoticed because people don't read them carefully enough, and so on. So the errors that become known are errors that other people notice because they are interested in this particular subject. So there are all the time errors, and we must have a systematic way of error correction. And the third one is that proofs are necessary for my own thinking. That means if I have a proof in the head, I have to write it down, sometimes to understand my own proof. Okay, I mean, first of all, to write down the proof is the best way to verify that you had the right idea. But in many cases, writing down the proof and showing the missing steps and what you should add makes your own idea clear to yourself. I mean, we don't. So mathematical thinking involves also paper and pencil and writing the proofs and so on. It's all the same thing. I don't think we can do without proofs. I mean, Ramanujan did a lot of things without proofs. There were also many mistakes there, and in any case, he couldn't communicate with his mathematical community because unless they were able to prove his results or to see them. And when they tried to prove, they found also that there is many mistakes. So proofs are unavoidable, and proofs should be effective. That means In principle, an informal proof you should be able to formalize it more and more and more and more. So in principle, a proof should be completely formalizable. Although in mathematical literature, this rarely happens, because it's enough to go a certain semi-formal proof to find out who was right.
I don't think this is the place to get into
Wait, Harvey, give me time. We can discuss it when you give the talk if we are still on the same line. Okay, so the question now is phi true? The second point. I ask, is phi true? And sometimes you can say, well, there's no matter of fact. You can adopt a system in which you make it true, and you can adopt a system in which you make it false. And this would be, in set theory, for instance, the continuum hypothesis is considered by quite a few people to be absolutely no absolute answer. You can have set theory with or without. They both are respectable set theories. And in the case of arithmetic, intuitionist, finitist, and related brands of constructivist position would give you this answer, that the answer simply says you cannot, the question is not meaningful unless I can prove an answer to it in my intuitionistic system or in my constructive system. So they are finitist system, and so on. And there is also ultra-finitism, but I don't want to enter into. This is a very interesting, complicated story. I think ultra-finitism can be made sense of, but I don't think this would avoid the difficulties here. Okay. So the general and anti-realist position is the truth value of phi is unknown because there is nothing to know. Okay, so this is. Now, this is not even an implausible proposition regarding, for example, continuum hypothesis. If you, in the same paper by Shelach, he implies such a position in some theory. I mean, he is kind of, it's not a philosophical paper, but he has some sort of pragmatic pluralism. Look, we don't have the best theory, we have a collection of theories partially ordered and so on. Now, if you believe that the continuum hypothesis has a unique answer, you should say, certainly the best theory is the one that gives the right answer. But he doesn't say that. He says you can do it this way, this way. There's a partial order between set theories. Now, there is the opposite, the wooden cape, and I don't want to go into this because set theory is not my concern here. Okay. So, now, what about the not particular sentence? Okay. So we can know that if a sentence is in psi, is a pi 1 sentence, if psi is in pi 1 and it is not a non-refutable pi 1 sentence must be true, and we can know it how? By some sort of meta reflection on what does it mean. If there was a counterexample, I would be able to prove the counterexample in the system, and provided that I can do, the system is sufficiently strong to calculate addition and multiplication. For instance, to have a counterexample to the Diophantine claim, all you have to do is to calculate addition and multiplication and have a counterexample. So if you have a system that sufficient for this, you could prove a counterexample and refute it. So the reason that we cannot do it absolutely is because we have to assume, first of all, that the system is consistent. And this itself is not provable. The story is well known. And the similar equivalent, the equivalent case for sigma 1, an unprovable sigma 1 sentence is false. Because if you had an instance, you could have proved that the instance and prove it. And so here there is a formal definition of minimally adequate, but I don't want to go into that. And where is, okay, this one here. I mean, I just put it here. You can prove in PA that every sigma 1 sentence, if every true sigma 1 sentence implies that it is provable in T what is minimally adequate, or you can put PA here itself. So this is a theorem of Peano's arithmetic that every true sigma 1 sentence is provable, and this theorem itself is proved from the outside by induction on the formula phi. So for every formula phi, you can show it. And I simply make this observation because I think this is the best way of having a transparent proof of Gödel's second incompleteness theorem to show that the probability predicate, the proof predicate is really a probability predicate.
Is it possible that T is minimally adequate, but piano arithmetic doesn't know this fact?
No, I assume, assuming, okay, yeah, no, right, but you know what, put PA instead of T and that you made my claim. Okay, I don't want to go, T would be a certain sub-theory, but put, instead of T, put PA itself. So this is, I think, the shortest way of getting to the Gödel's second incompleteness theorem without too much hand waving, which usually it takes.
I was thinking of T as Haim Gaifman, piano arithmetic.
Okay. Now, let T be our adopted theory and define continuous iteration of the consistency claim. I use here CONT. I use it in the meta language and in the language. So it's a formula, but I will also use it in the meta language. So con T means T is consistent. Con 2 to the square T is con of con T, but it's con T plus con T because you have to have a theory there, and so on. So this is an iteration of consistency. And say that we know A once we have derived A from some con to the power n A. Okay? Con to the power n T. Okay, so the reason is we believe our theory is consistent, so, and therefore this is also consistent and so on. You can iterate this n times. Of course, the more you iterate, the weaker is your knowledge, so this is degree of knowledge. So if you want to, and you can continue this going through the recursive ordinals, taking unions and so on. At some point you will use CE, and so the whole thing is rather vague, but this is how knowledge goes. So for my purposes, I will just take all the finite iterations of con and T and say, in a kind of a vague way, that even if I cannot prove it in the theory, but if I observe that it follows from some con and T, then I know it is true. Okay. For pi1 sentences, knowing that they are irrefutable leads us to knowing their truth. So this is a way of making precise this claim, because we can derive the truth from con first on the first level. And similar for sigma 1 sentences. So, however, using the fixed point technique, we can construct sentences known to be undecidable, whose truth value is at present unknown. We cannot.
What do you have in mind?
Okay, you should know that because I asked you and you gave an answer. Okay. Okay. So this is done by involving other sentences whose truth value are in present unknown. That means you can smuggle into it some open hypothesis, and so you can construct a sentence which is not pi1 and not sigma 1, but a disjunction of a pi1 sentence and sigma 1 sentence, which you know for sure is undecidable, but you have no idea what the truth value is, because this sentence refers to some open hypothesis in a kind of, and this causes you at present not to know its truth.
What is the present?
Wait. Look, there will be time for questions. You are cutting into.
But in the future, I don't know what the present is.
At present, that means so far we haven't solved the hypothesis, so I don't know.
You mean today?
Today.
Okay.
It's always today. Okay. So the question of doing something like that, I mean, about 9 years ago, I put this question in on FOM, hardcore, and so on. My idea was that perhaps we can distinguish between gather kinds of undecidability and undecidability in set theory, that in set theory you really have a hard core, but the gather you always know, and is there a general way of doing it? And then Torkel Franzen unfortunately died recently, and Harvey let him go on and flourish, as we say in Hebrew.
My God.
He gave me examples, and recently Joel Hamkins gave a very nice example, the simplest example of this, which he knew that there were examples, but he found our simplest case, and here is a sentence: square T implies con T and conjunction alpha. Take any alpha which you don't know. And then this sentence you can prove from con square T, you can prove that it is neither provable nor refutable, but because this you can know, but once you will know the truth value of alpha, you will say this sentence is actually equivalent to alpha. This sentence turns out to be equivalent to alpha, so you don't know if you know it, but you can show that it is undecidable. Okay. So this is okay, and there's even a simpler sentence is alpha star. The Rossa sentence for T, I don't want to go into the Rossa sentence. The Rossa sentence is a sentence which is weaker than continuity, but still not. It's weak. It's implied by continuity, but the sentence itself. But I'm sorry, consistency. Okay, my association is here. Somewhere is in continuity. No, CONT. Okay. It is implied by con T. It's weaker. It's known to be strictly weaker than con T. But if T is consistent, then the sentence itself cannot be proved nor refuted. So this is the Rossa sentence, which play a particular role there. And this is the simplest example that I can have. And in this case, the equivalence follows from CONT, the equivalence of this. Okay, so there are particular cases, but they are not helpful because you smuggled here something else. So, and the idea is, can we get rid of this smuggling? Can we define precisely what does it mean not to smuggle something else? Okay, and I posed this question and there was no answer, but actually I think we can, so the sentence is of the form phi op psi, phi belongs to sigma 1, psi belongs to pi 1, and we don't know, if you knew an instantiation of phi, you will know that the whole thing is true. So if you don't know any instantiation of t, the whole thing reduces to the sentence in pi 1, but since you don't know phi, whether phi is true, the whole sentence remains undecidable. So there are such examples. On the very next step, you don't even have to go to pi 2 sentences. You can take the simplest Boolean combination here and to get this kind of examples. So we do not know whether in the future we'll know phi or not. So it's in a certain sense a question which is at present unknown. Okay. Now this is where appeal to probability logic, sentential logic perhaps might help, and other versions of probability logic in which Sergey is the expert here. I'm far from an expert in this. I know very just the basic. And in probability logic, you can define con and in this standard way, and we know that we can construct fixed points, and these are well-known results. My conjecture is that if alpha is known to be undecidable in probability logic, you can say if alpha is known, that means if you can iterate the box n times and you know that it is undecidable, then you should know its truth value. And I think this should either be known or derivable from known results. So this is my first conjecture, technical conjecture. And the big question is, can this be generalized to provability predicate logic, which would be really the nice result? Or if you don't want to smuggle in things from Peano, you can actually consider probability logic built on top of Pressburger arithmetic. So you have enough natural numbers and you can compare perhaps lengths of proofs in this, but still you cannot smuggle in this alpha. So this is my first technical item. Now let's consider the following sensational scenario. This would be really an earth-shaking results. The twin prime conjecture, a proof is found that it is independent of ZFC. Okay, and not only this, but the proof doesn't give you any idea whether it's true.
So a con ZFP implies con that's independent, assuming that ZFC is.
Yes, yeah. Yes, right. If ZFC is independent, and it doesn't give you a hint how the proof is. And let's show how, in principle, such an example can be proven. So you construct two models of set theory. This is a model theoretic thing. You construct two models of set theory. One model the numbers satisfy it, and the other model doesn't satisfy it. Obviously, these are not omega models. In both models, the numbers are non-standard, but you don't know. It doesn't give you any idea of it. So it's possible this would be a sensational. This is way, way beyond we can dream. Just think about Paris Harrington and the things that you know, not provable in Peano. This is, or even for bounded arithmetic, these are very difficult results.
Why do they both have to be non-standard?
Because if one of them was standard, then in that model, you will have the answer. One of them satisfies the twin prime, the other doesn't satisfy the twin prime. If one of the models were standard, then this is a model which gives you the truth value of the twin prime. Therefore, both models must be.
We don't know which one is standard.
Well, that's another. Okay, suppose it's obvious that both of them are non-standard. Yeah, you might have even a meta construction in which you constructed the model and you don't know. Let's assume you're right. We might not know. Okay, now, are we prepared in the face of such a result to say, well, we have two legitimate conceptions of natural numbers. In one conception, there are infinitely many, the twin prime goes all the way. In the other conception, they stop at a certain point, and both of them are equally. Okay, this is kind of a test question for you to test your realistic conception about the natural numbers. So in Pi 2, you might even start to doubt. If there is some results, maybe some people will say, we really don't understand the natural numbers. That's a possibility. I don't think I will subscribe to that, but in set theory, I'm willing to subscribe natural numbers. No, why here and here the difference? This is a long, complicated question and very debated, and this is not my topic today, but this is still a possibility here. What I want to point out that when you come to Pi 1, there is no such possibility. Okay. Once you have proven it that it is undecidable, it's true. So in the Pi 1 level, this is immune. Okay. Now let's go to the possibility that we will never know. There will be always Pi 1 sentences, which in principle there are Pi 1 sentences, which in principle are unknowable to human beings. And this is what Getter called absolutely undecidable sentences. I don't want to go to read this, but I want just to sum it up for you. So Gödel says, well, look, it's possible that the human mind extends any possibility of any finite machine. By finite machine, he means a computer. It's possible that human mind is something that you cannot, and it is possible that the human mind can solve every mathematical question because it simply transcends the computer. We can know things. In principle, we will be able to know things And that means there might be a sequence of theories, one becoming stronger and stronger. We get more illumination and so on. So in principle, everything. So this is one case. In the other case, well, there wouldn't be an infinite. Perhaps at any stage there will be unknowable problems. It might be that there must always be unknowable problems. So these are the two alternatives. And he said maybe even both of them, we transcend the machine, but still there are unknowable problems. But he was bothered by this possibility, mostly with regard to set theory, but he also considered in this context number theory. So I think this is a very doubtful scenario, which I can sum up like this. Okay, so it's really a kind of scenario about the evolvement of human intelligence. I mean, I think it's, so you have a sequence of theories. At the end, you have all mathematical truths, and there you have the human being who knows all mathematical truths, the limit of all these things. So I think there is an alternative hypothesis that, yes, we can develop theories, but somehow the human brain is limited to producing a certain sequence of theories. Of course, we don't know the algorithm, we don't know anything about this sequence. We are in the sequence, but this is as plausible. So, according to my view, I think Saul Pfefferman wrote, I think in the 90s, a paper arguing exactly the same line of argument, that it's not clear even what the hypothesis is. I think the hypothesis has become the hypothesis about something, human evolution, and so on. I think we'll better assume that we have some theory and argue within this. We might extend set theory by axioms here and there, but this scenario I don't think should be taken too seriously. Now, the point number, I think this was point 4. Are these things too long? Are the undecidable things too long? We simply cannot read them. Here is a prescription how to make short ones. I don't want to go into them. I use Diophantine equation theory and things like that. You can get a Diophantine equation, which is not using the latest development in the Diophantine Matasevich, since Matasevich and so on. You produce a universal Diophantine set, and you can. What will happen there? That there will be fixed parameters in the Diophantine equation, which are very large, but we can always write large numbers using several exponentials and so on. So the Diophantine equation will be weird, but it wouldn't be longer than certain Diophantine equations that have been considered in the mathematical literature.
I don't think that's correct.
Okay, okay. Now, the main worry is the following. So I think you can have sufficiently short one that you can read and understand. I mean, in principle, suppose you have Diophantine equations on several pages, but still, this is not a book. You can read it and you can make sense. You can say, well, do these Diophantine equations, point to this, do this, have a solution. I think this is feasible. Now, the main worry is the following. A mathematician tries to prove a theorem, or tries to solve a problem, unknown problem. You see, maybe the problem is simply undecidable, and it might even be a P1 problem, and a lot of problems are P1 problems, and he simply won't be able to get an answer. The sentence is true, but you won't be able to get an answer simply because it is in this damned sequence, and there is no other reason for it. It's brute force. It is simply there, and you cannot solve it. It's not that you know an undecidability results like in set theory, which you can give a reason why you cannot solve it. This is brute fact. It is just in this one, and you have no insight why it is unsolvable, true but unsolvable. So let me jump ahead, since I'm getting short on time. How much more time do I have?
Maybe minus.
Minus? No. Oh, come on. Okay, so let me, okay, fine. Look, I have 5 more slides, but I have 5 more slides. I won't haggle, but at least for that, give me just to sum it up here. I end up, the last slide gives you a list of problems, famous problems in mathematics, which are in various algebraic geometry and so on, starting from the Riemann hypothesis, which are P1 problems. And there are some other problems which are P2. There are hundreds of problems like this, which are P1, P2, and which some of the famous problems we don't have a solution. Now I want to single 2 problems out of these problems, which are P1 problem, the four-color conjecture and the Kepler conjecture. Okay. Both of them are P1. I mean, the four-color problem is easily seen to be P1 even before the solution was found. So what happened there in this? They were solved. I mean, the second one is not solved, but it's a big project to solve it using computers. And the first was solved by heavily use of computers. That means a human being cannot understand actually what the problem is, but it is acceptable that the solution is right. What happens there? They found out that it's okay, but there are about 1,700 special cases of graphs, some of them not at all trivial and so on, which you cannot verify. So you give it to the computer to calculate, and he found out these are okay, so the problem is solved. The Kepler conjecture is even more dramatic in this respect, because
on the four-color there's some big simplifications that came out.
Yes, but still doesn't eliminate. The simplification was in getting simplified and getting a proof verifier which convinced people that the computer didn't make a mistake. It still remains a problem which is solved only by computers in principle. The Kepler is even more dramatic, because there it's to find a way to arrange ball in, say, you have a box, how to arrange ball to get the maximum efficiency. And they found out that except for very weird arrangements, which are finite in number, there is a bunch of arrangements in a certain range in which you cannot do it. If you knew for all other arrangements, you can do it. But these arrangements, you had to solve about 100,000 linear equations and things like that to find out this. And that's why you couldn't do it. Okay, this means that in principle there can be hard, almost empirical facts in mathematics that you have no insight into them. This is in the finite case. These are problems which are solvable. You can have empirical problems, almost empirical problems, quote, in mathematics, you have no insight in them. Now suppose God, who knows the whole thing, comes and tells you, you know, it is just so, you know. Riemann's conjecture is true, just so. I cannot explain it to you. It's like this thing of irregular bunches that you must go and really check it. Suppose I tell you there are 25 primes smaller than 100, and there are 46 primes smaller than 200. Why? And I say, I don't know, it's just so. Go and compute. There's no reason for that. There is no general reason for that. Just go and compute it. And this is in the finite domain. In the infinite domain, this sequence raises a possibility, says some, if you are a realist about the infinite domain, about actual infinity, that there are problems like that that remains forever unsolvable, and this is a worry. And the last, I will give up the last more technical thing about the lattice of all true pi1 sentences, some conjectures and my partial result that I have. So that's it. Thank you.
What's your position? I don't really understand your position on some of these matters. For example, most importantly, let A be a large cardinal hypothesis. Now there's small ones, medium ones.
Okay, right.
So maybe your position might change according to whether it's these big ones, medium ones.
Okay.
So let A be a large cardinal.
Okay.
process. Consider the statement consistency of ZFC plus A.
Okay.
Or.
Okay.
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 What is your position on that? Is that an absolutely unknowable, or what is it?
No. That's a different. Here you are asking a question in arithmetic. The consistency of this is an arithmetical question.
Yeah.
And even if I don't, this is an arithmetical question. Now we have a lot of intuitions about reasoning in set theory. For instance, I believe that ZFC is consistent, although I don't have a realist position with respect to everything which is stated in ZFC. So we have a lot of experience with these ways of reasoning. We have a lot of accumulated evidence. So I think I will bet on it that it is consistent.
What, for which A?
Huh?
Which A? I said a range of large cardinal
Oh, you want me to give you
And also
exactly?
about-
You want me exactly to give you? I will to give you that.
Don't get out of it that way.
I will give you up to super compact will be okay. Up to super compact, I will do bet. After that, I don't know. I mean, with Reinhardt thing, I don't know.
The point is, first of all, you haven't answered my question. Is it unknowable or not? That's the first question.
Whether it is considered, I don't. This I do.
Is it knowable or not knowable? Do you know whether it's knowable or not knowable?
No, I don't. I don't know. I don't. I'll tell you why. I'll tell you why. Because this is a question that makes sense, in a sense. And one, to prove that it is consistent, I might go to some second-order theory and so on, which I do take seriously and prove it in that.
Or you consider that knowledge?
Yeah.
Okay. I just want to get your position.
Knowledge is never knowledge.
I don't want you to dodge it. I want to get your position.
Okay. So I ask you what you consider. Okay. And my knowledge,
I have a forecast idea. I wouldn't give this talk.
You wouldn't give this. Okay, fine. Okay. So I think that knowledge itself comes in degrees.
Okay. This wasn't clear from your talk.
Okay, now, look, I cannot present all the nuances. I wanted to present the thing in gross lines. Even here,
This is a very important thing you just said.
No. What I said is knowledge comes in degrees. I think that there is no question. Well, I said it when you say, when I iterated the box there, the Kant thing, I said knowledge comes in degrees.
I was too dense to get it.
Okay, fine. So that's what it implies. And knowledge in the case of certain basic combinations, like the 7-bridge problem, that is true. But after that, I will take there are certain knowledge which are rock bottom. I don't understand what is not to know.
Okay, so your picture, I want to get the guy from picture.
Okay.
If you take, for example, consistency of A, where A is a large cardinal,
Right.
so it's going from this big all the way up to the wildest ones,
Okay.
You probably believe that there's some knowledge there,
Right.
and it's decreasing quality of knowledge. Is that
It's
right?
decreasing certainty.
Decreasing certainty,
Right.
down all the way up to maybe if you take the highest, the most wild of the large cardinals, the ones that are known to be inconsistent with the actual choice.
Yeah, the Reinhardt, the Reinhardt axioms.
Yeah,
something like
there
that.
the level of certainty is very low.
Look, there was a conference, we had 2 weeks ago, there was a conference in Bristol in which the top set theoreticians were trying to prove that negation, just this, and they failed. So this gives me an indication that it might be consistent if you eliminate the axiom of choice. Without the axiom of choice.
Vaughn, you have something aside to take?
I suppose it's a bit related, except that it's on the algebra side rather than the logic side. And that is that there's a result in 1980, proved by Lantek and Scott at the 70th birthday fetch trip for McLean, that the natural number object in the free corpus is is a standard, whereas in the free Boolean corpus, if you want to play classical logician, as Haim likes to do, it contains non-standard numbers. So if you get to look for non-standard numbers, it's better to be a classical logician than an intuitionistic logician. So that's where I would recommend you get to look for your non-standard numbers.
Well, I ask you, what are non-standard numbers?
Yes, well, that's what happens in the free turbos. You get to play games.
Yes, but you should, look, you know what? I don't know what your natural numbers are. If you understand the distinction between standard and non-standard, I will tell you, my notion is standard.
Yeah. Oh, it is, and it's standard in the free turbos.
So in the C topos, they are non-standard, and therefore they are not standard, that's all. I believe, I mean, the point is not if we want to speak about non-standard numbers. The point is whether we know the distinction between standard and non-standard. And if I tell you, for me, numeric truth is by definition a numeric in the standard, that's fine. If you want to include non-standard, be my guest. I mean, I myself worked a lot.
I'm just pointing out the non-standard classical notion.
Non-standard is a classical notion.
In the sense that you're working in a Boolean. If you work in a Boolean topos, then you get non-standard natural. The natural number object contains non-standard numbers.
Okay, so the Boolean topos doesn't make sufficiently fine distinction.
Yeah.
Okay.
We are running out of time in our standard universe. I have two fast announcements. One is that there's been a change in the schedule for Friday, and you can pick up a revised version outside. The other is you're on your own for lunch. In your folders, there's a list of local restaurants, and there's also a very nice cafeteria on the 8th floor of this building.